Microseismic data often provide the best view into what's actually happening in the downhole environment while horizontal wells are being completed or refracked to stimulate production in tight oil and gas reservoirs. DI Transform offers a rich suite of tools to allow operators to visualize and interpret their microseismic monitoring data in an integrated environment, that is, in the context of all their associated geologic, geophysical, and engineering data, and to feed the output from that interpretation into a powerful statistical analysis package. This video will provide an overview of the workflows that allow you to import and visualize microseismic events and time series treatment data, analyze the events to estimate stimulated reservoir volume, compute and cross-plot microseismic event attributes in our data analysis workflow, and extract rock properties from seismic volumes onto microseismic events for use in advanced analytical workflows. We'll start with a new project into which we've imported well, treatment, and microseismic data. Shown in this 3D scene is a horizontal well that was completed in 3 stages, while geophone arrays were deployed in 2 nearby vertical wells to monitor microseismic activity. In this view, the 3 treatment stages are shown as the red and blue cylinders aligned with the wellbore, and perforation locations are shown as the black spikes protruding from the treatment intervals. We now add in the microseismic events that occurred during stages 1, 2, and 3, with each event colored according to the stage and sized relative to its magnitude. Event magnitudes, along with any other available event properties, can be imported along with event locations. As we rotate the view to see the distribution of events in 3 dimensions, we can already see significant differences in the reservoir's response to fracturing these 3 stages. To further investigate the microseismic response in the context of our engineering data, we can launch a time display that will allow us to plot time series data along with the occurrence of microseismic events as a function of time for each stage. The time series shown here are slurry flow rate, surface pressure, and proppant concentration in green, red, and blue respectively. Microseismic events are plotted at the distance from the wellbore to the event as a function of time. Now we'll enable time playback mode and start watching the progression of our fracture stages as pressure and flow rate increase and the reservoir begins to fracture. It becomes clear from watching the data in this view that there was significant overlap between stages 1 and 2, and even stage 3 triggered a moderate level of microseismic response toward the toe of the wellbore rather than the heel stage that was being targeted. This view can give operators clear insights into the effects of engineering parameters on microseismic response and may highlight issues related to poor stage isolation or problematic channeling of injected fluids into pre-existing faults. We may be able to identify cases where better isolation and refracking of some stages might pay off in increased production. To give us a more quantitative view of the distribution of microseismic events and energy released along the perforated interval, we can use the microseismic functions built into Transform's well log viewer. This 3-panel view shows a gamma ray log on the left, microseismic events plotted as a function of measured depth on the vertical axis and magnitude on the horizontal axis in the middle panel, and event density as a function of MD on the right. In the event density plot, we can see that the microseismic response from each of the 3 stages was very different. Stage 1 triggered relatively little microseismic activity, with the majority of the events occurring beyond the toe of the wellbore. Stage 2 was a little more active, but fracked back into the stage 1 zone. Stage 3 stimulated the greatest microseismic response, but again, much of the activity propagated backward and happened in the vicinity of stage 2. The large spikes in the seismic moment log, shown as the black filled curve, indicate that the majority of the microseismic energy release occurred outside of the perforated interval. This suggests that large pre-existing fractures may have been reactivated during treatment, possibly robbing the targeted zone of proppant and decreasing the effectiveness of the frac. We'll next take a look at the stimulated rock volume workflow that will allow us to calculate stage by stage and summary volumetric estimates. We'll first put our scene into microseismic analysis mode, then create a new microseismic analysis to hold the results. This launches an interactive dialog where we run a 2-step process, first calculating a density volume, then a geobody that encompasses the portion of the microseismic event cloud that we desire. In this case, I'll choose to weight the value contributed to the density field by each microseismic event by the event's magnitude, under the assumption that larger events correspond to larger fractures. Note that any other microseismic event property can be selected to weight the events instead of magnitude. We then compute an event density field, which immediately appears in our 3D scene and can be sliced by manipulating the box that surrounds it. The density field clearly reveals that microseismic activity was heavily skewed to the northeast of the targeted zones during this treatment, suggesting that the reservoir to the southwest may have been inadequately fractured and drained. Once we're satisfied with the event density field, we can adjust the threshold that specifies the minimum density of microseismic events that we require to include a specific portion of the reservoir in our estimated stimulated rock volume. Moving the slider to the right causes areas of lower event density to be excluded from the SRV. We can also optionally restrict the SRV to include only areas bounded by any horizons or aerial regions defined in this project, giving us fine-grained control over our eventual volumetric results. In this case, I'll leave the geobody unbounded. When I push the Create Geobodies button, the system automatically creates individual geobodies for each stage in this fracture job, as well as a summary geobody for all stages. Volumes, aerial extents, and the number of microseismic events included in each geobody are reported and can be captured for use in analytics workflows. We might, for example, include the SRV volumetrics in a model that attempts to predict production as a function of engineering parameters and microseismic response. Next, we'll take a look at the microseismic data analysis capabilities in Transform, which provide a nice set of tools to analyze and subset our events based on an array of event properties. We'll launch the cross-plotting tool from the top-level menu and arrange our views so that we can see the 3D scene at the same time as the cross-plot. On the left is a list containing all of the microseismic event properties available in this project. Some of these were imported along with the events. Others, such as event density and distance to the wellbore, are computed automatically at import time, and some have been created either in the microseismic properties calculator or by extracting values from seismic volumes onto microseismic events. We'll take a look at that workflow later in the video. Let's first plot a measure of the confidence in the event locations, as provided by the vendor that processed this microseismic data, against event magnitude. As we'd expect, there's a positive correlation between magnitude and confidence due to the fact that larger events will produce a stronger seismic signal and are therefore easier to detect and locate. Now we'll draw a polygon around these higher quality events, and those events are automatically highlighted in the 3D scene. And as I move the box in the cross-plot, the scene updates to show the included events. Once I'm satisfied that I've selected the group events that I want, I can create a new microseismic analysis using the toolbar in the scene that includes only those events, which I might then use to create a more conservative estimate of SRV. Another type of data analysis that's made possible by Transform's integrated data workflows is a cross-plot of seismic attributes versus microseismic event properties. If I have 3D seismic data available in my target area, I can quickly extract summary values at the location of my microseismic events from any of my seismic volumes and save those values as properties on each event. In this case, I'll extract the curvature value interpolated onto each event from the 4 nearest traces in my seismic volume. The curvature value can then be plotted against any other event property, in this case I've chosen magnitude, to investigate relationships between rock properties and fracturing. And finally, we can add the seismic data into the scene to allow us to visualize the 3-dimensional relationship between the microseismic events and any seismic property at the same time that we're quantitatively analyzing the relationship in the cross-plot.